I'm sharing my screen. So frequency divided by 2 circuit. Just I will open this PPT. I'll explain along with the coding part. Mm, so so this is frequency divided by 2 circuit. Okay. So frequency divided by 2 circuit. If you take yeah, 1 second. I will take my pen and pad. So here, so what we are doing means like here what we are doing means like a Q bar is there. Q bar is connecting as a D input to this D flip flop. So every time what happens, suppose initially like Q is 0, Q bar becomes 1, okay, and D becomes 1. At the next clock pulse, what happens means this D is given to the D input is coming to during this passage of clock. D input is coming to Q. Okay, so now Q becomes 1. Q becomes 1. Q bar becomes 0. Again, D becomes 0. Okay, at the next clock pulse, what happens? At the next clock pulse, again this 0 will be coming to Q. 0 will be coming to Q, and as q is 0, here q bar becomes what? Q bar becomes 1. Q bar is connected to D means this is 1. Okay, and next clock pulse, this D is there, no, this D is coming to Q. Q becomes 1, and Q bar becomes 0, and becomes 0. Okay, and at the next clock pulse, what happens? Again, D value will be coming to Q. Again, Q bar becomes 1, and D becomes 1. Okay, so here what happening? That means let us take this clock cycle is T. Okay, so clock cycle is T. Q output clock cycle becomes how much? Let us take T dash. This is T dash. Okay. So T dash equal to what? 2T. T dash equal to 2T. We know that time and frequency are reciprocal. So that means 1 by F dash equal to 2 by F. Okay. So if you reciprocal, that means F dash equal to what? F by 2. So this circuit is acting as frequency divided by 2. Do you understood how I am analyzing? Any doubts or queries in this? Okay, so this is a simple example like I'm taking f equal to 1 by t. So total master clock is 1 nanosecond. So frequency equal to what? 1 by 10 power minus 9. So 10 power 9 means 1 gigahertz. Okay, so frequency divided by 2 means what? F equal to, that is 1 by t. 1 by 2 into 10 power minus 9. 0.5 into 10 power 9 means frequency will be zero point 0.5 gigahertz you are getting. Okay, this circuit is acting as a frequency divider circuit. Okay, so mm, for this I wrote the Verilog RTL code. I am opening that RTL code. I will show you in the Vivado also. That is frequency divided by two circuit. 1 second. Frequency divided by two circuit. Sequential circuits. Frequency divided by 2, and even number, and this is frequency divided by 2. Okay, so this is my RTL code. So if you see this RTL code, frequency divided by 2, I am declaring input clock underscore in, input reset, input clock underscore out. So always at the rate passage of clock or passage of reset, begin. If reset, so if reset equal to 1, begin, I am initializing clock equal to 0, end, else begin clock equal to not of clock. Okay, non-blocking with toggling condition, that is clock out equal to not of clock. Okay, so this is my design, and coming to the test bench. So this is my test bench. So here clock underscore in reset I need to declare with reg data type, and clock underscore out I need to declare with y data type. So I need to instantiate my design in the text bench. So this is my design name followed by the instance name, and this is connection by name. Okay. After this, you need to generate the clock. Always hashtag clock equal to not of clock. And in initial begin, first I am applying clock equal to 0. I am asserting the reset. After that, after 15 time units, I am deasserting the reset, and I'm checking for 100 time units. That means 10 cycles. I'm checking the waveform whether I'm getting the frequency divided by 2 or not. Dollar finish means you need to finish the simulation. Dollar monitor means you need change in the variables, then it will display. Okay, so this one I'm going to display in the, and it's going to see in the Vivado tool. So I'm opening the Vivado tool. So file, project, new project. Next, I'm creating the project frequency divider circuit. Okay, frequency divider circuit, and I need to choose the folder where I need to store the uh, file. Okay, so uh, in this I need to select RTL G11. We can batch and RTL codes using Xilinx Vivado. Select next. Next, I need to create my file name. So here you see this is the frequency divided by 2 circuit. So copy this and here you paste and choose the location. RTL codes using Xilinx Vivado. Select, select. Here I need to choose the location. No, I created the frequency divider circuit. Select. OK. Next. Next. Again next. Finish. OK. Yes. So here frequency divided by 2 circuit. Okay. So next this code is there. No, I'm copying and here I'm pasting and save the file. So next to go to the test simulation test bench I need to add. So this is my test bench. So this is my test bench file. Right click copy and here next create the file name, choose the location, frequency divider, select OK, finish, OK, yes, and my simulation test bench file is created. So just this code, just you copy and paste here, paste here, and save. So my test bench file is instantiated in my design. Run simulation, run behavioral simulation. So you can see in the uh, monitor TCL console also. Or if I see in the simulation part, you can understand. See here, fit to page. So when reset equal to 1, the clock out equal to 0 only. So when reset equal to 0, here what is happening? So that means during one cycle, you are getting half cycle. Okay, during one cycle, you are getting half cycle. And during this one cycle, you are getting half cycle. Okay, so that means time period. So here, this one time period equal to what? You are getting two time periods. So that means time is doubling, frequency is divided by 2. Okay, so just you can zoom this, you can see over here. So from 10 cycles and here 10 cycles, total 20 cycles. It is taking 2 cycles, but here it is taking 1 cycle only. So as the time period is double, frequency will be half. Frequency is divided by 2. Do you understood how I am analyzing? Frequency divided by 2 circuit with 50% duty cycle. Did you understood this? Shall I move forward? Oh, yeah, yeah. Okay. Next. Next, next is, so our agenda is you need to develop a frequency divided by f by n. So where f by n, where n is a odd integer and n is a even integer. You can try with this if n is a decimal value. Okay. I will explain when n is a odd integer and n is a even integer. Okay. So first I will design f by 3 circuit. Okay. So when you are designing f by 3 circuit, you need to use which counter means mod 3 counter. Okay. So you need to use which counter? Mod 3 counter. So mod 3 counter means this is off for how many cycles? 2 cycles. This is on for 1 cycle. Okay. So there is a term called duty cycle. Duty cycle. What is duty cycle? Duty cycle is T on by T on plus T off. Okay. T on by T on plus T off. So that means here how much you are getting? Duty cycle 1 by T on is 1, 2 plus 1. Okay. Into 100. Percentage is into 100. So you are getting 1 by 3 into 100. So that means you are getting 33.33% duty cycle. Okay. So actually we will not prefer this 33.33% duty cycle. So if you observe here, so that means here this is on for one cycle. This is on for one cycle. Okay. And this is off for two cycles. Okay. So this is what this is 33.33% duty cycle. Okay. So but you want how much of duty cycle means 50%. 50% means what? 3 by 2. 3 by 2 means what? 1.5. It should be on for 1.5 cycle and it should be off for 1.5 cycle. So that means you need to alter the output frequency by zero point 0.5 cycle. You need to take out point from zero point 0.5 cycle from here. Okay. So for this, what you are using means you are using negative edge trigger D flip flop. Negative edge trigger D flip flop. Okay. So when you use negative edge trigger D flip flop, and this is the output of mod 3 counter, and this is the output of negative edge trigger D flip flop. This is given to OR gate, then you will get the F by 3 circuit with 50% duty cycle. 50% duty cycle. Okay. Yeah. Just one minute. హలో
హలో
చెప్పు.
ఏం చేస్తున్నావు అబ్బా?
నేను క్లాస్లో ఉన్నా.
సరే ఓకే, నేను అన్నట్టు ఉన్నా.
Yeah. So here if you see, so that means here, so this is what, this is not 50%. This is what 33.33% duty cycle. Okay. So here you are using negage of D flip flop, no? So here what is happening? That means this is negage means this is actually, this is passage. Okay. So this is passage. This is passage. Actually, this is negage. This is negate. When it is going from 1 to 0, this is negate. Okay. So during this negate, whatever the Q1 is there, you are getting the output. Q1 is 0, you are getting 0. And during this negate, whatever the Q1 is there, you are getting the output. Here 1 is there, here 1 you are getting. And again during this negate, again Q1 is 0, it is going to 0. Okay. Again during this negate, Q1 is 0, it is going to 0. Again during this negate, Q1 is 1, it is going to 1. Okay. So such a way that you need to do the OR operation. So if you see the OR operation, 0 or 0 means you are getting 0 only. 1 or 1 means 1. And here 1 or 1, here getting 1. 0 or 1 means here you are getting 1. Okay. And here all are zeros only. Okay. So if you observe here, so that means so this will be high for how many cycles? This is one cycle. This is one cycle, and this is how much? Zero point 0.5 cycle. Okay, one cycle and 0.5 cycle. That is 1.5 cycle. Okay, so this is on for 1.5 cycle, and this is this is off for how many cycles? So this is one cycle and this is zero point 0.5 cycle. Okay, so zero point 0.5 cycle. So 1.5 cycle, this is off. So what is my duty cycle? Duty cycle is on 1.5 by 1.5 plus 1.5 into 100. So that means here this is 1 by 2. Okay, 1.5 by 3 means 1 by 2 only, into 100 means you are getting 50% duty cycle. 50%. So that by using native edge trigger D flip flop, you are converting your circuit into 50% duty. A by 3 circuit with 50% duty cycle. You are getting it 50% duty cycle. Did you understood how I am analyzing? Okay. So to alter the output frequency by zero point 0.5 seconds, zero point 0.5 cycles, you need to use negative edge trigger D flip flop. Okay. So for this, I am writing the code. Okay. So for this, I am writing the code. Yeah. For this, I am writing the code. So here you see F by 3 circuit, no? F by 3 circuit. Yeah, this is F by 3 circuit. First, first what I need to design? Mod 3 counter I need to design. Okay, module divided by 3, 50 DC. Input clock, input reset, output Y. So count is 1 down to 0. Why? Because 2 bits are there. No, so 1 down to 0 count. And here Q1 is there, no? So this is Q1. Where is Q1? Q1 I'm initializing with Q1 and Q2 is there, no? So that those are I'm initializing. Okay. So here I'll close this. So Q1 and Q2, these things I'm initializing. Okay, Q1 and Q2 I'm initializing. Okay, and next I need to develop the Mar3 counter. So Mar3 counter means what? It should count from 0, 1, 2. Again, it will roll over to 0. Always at the rate passage of clock or passage of reset. Begin. If reset equal to 1, begin. Count will be initialized to 0 and Q1 will be 0. Else begin. If count becomes 1, 0, that is the count is coming to 2, count becomes 0. Count becomes 0. Else count will be count plus one tick by normally it should count. Okay, and q1 is non-blocking with count equal to 2 tick binary 0 0. So by this I am developing the mod 3 counter. Okay, and after that I need to develop the negative edge trigger D flip flop. Always at the rate negative of clock or passage of reset. Begin. If reset equal to 1, q2, that is the output of negative of flip flop, q2 equal to 0, else q2 equal to q1. Okay, this is developing negative edge trigger D flip flop. After that I need to use continuous assignment statement, that is assign. So q1 and q2 is given to which gate? OR gate. Okay, so that is assign y equal to q1 or q2 end module. Okay, so this is frequency divided by 2 with 50% duty cycle. And coming to the test bench, I told you have 5 steps. You need to declare the internal variables. So clock and reset with reg data type and y with y data type. And you need to instantiate your design in the test bench by connection by name. And next you need to generate the clock. Okay. And you need to give the stimulus. Initial begin reset equal to 1. After 20 time units, you need to release the reset. Observe the output for how many cycles means 200 cycles. 20 cycles you need to observe. That means you need to give 200 nanoseconds. Dollar finish end module. Okay. If this code is fine, any doubts or queries? Shall I move forward? Yeah. Okay. So just here this module is there now. I'm copying this and go to the design source, create the design source. Next, create the file name. Okay, and choose the location, frequency divider, select. Okay, finish. Okay, yes. So I'm creating the design source, frequency divided by 2. And next, this one, design code I'm copying, and next, here I'm pasting, save, and go to the test bench. This module name is there, no? This module name, copy, and here. Go to the simulation sources, add the simulation sources. Next, create the simulation sources. Choose the location, frequency divider circuit, select OK, finish. OK, yes. Okay, I created this test bench. Okay, this is TB file. Okay, so this TB file select all, copy, and next here you paste, save, save, and next right click, set as top module. Right click, set as top module, run simulation, run behavioral simulation. So if you see here in the simulation part, I'll zoom this. I'll zoom this. So when reset equal to 1, what happens? Y equal to 0 only. And when reset is equal to 0, here you observe this is high for this is one cycle. Okay. And this is half cycle. So this is high for how many cycles? 1.5 cycles. Okay. If you zoom this, you can see here easily. Yeah. So here this is one cycle and this is half cycle 1.5 cycle, and this is one cycle and this is half cycle 1.5 cycle. So this is on for 1.5 cycle and this is off for 1.5 cycle, so that you are getting 50% duty cycle. Is it fine? Any doubts or queries? You are getting 50% duty cycle now by F by 3 circuit, 50% duty cycle. So this is on for 1.5 cycles and this is off for 1.5 cycles. Shall I move forward? Actually, like inside there are frequency divider circuits. Okay, so that means so many like different micro means different modules will be there. Inside there will be some I2C, RAM, or ROM, or if you take SOC, okay, different modules are there. So all modules doesn't operate at same frequency. Okay, there will be some master clock. In that master clock, inside there will be a frequency divider circuits. That frequency divider circuits will divide the frequency such a way that in order to synchronize, all the frequencies should be operated at 50% duty cycle. For the synchronization purpose, we are making that as a 50% duty cycle. Synchronization. We need to synchronize all the peripherals with respect to suppose if you take CPU. CPU have ALU and memory unit, process control unit and bus interface unit. Okay, in the memory unit also you have RAM, ROM, all those are there. So means we can't say that all the peripherals are not operating with same frequency. There are different frequencies. Inside some PLLs are there. That PLLs will divide the frequencies, multiply the frequency or divide the frequency, such a way that in order to synchronize, they should operate with 50% duty cycle. Is it fine? No, no, no. Synchronization will not happen. It should operate with that frequency, whatever the frequency, with the 50% duty cycle. Okay. Yeah. So next, I am designing frequency F by 5 circuit. So F by 5 circuit, if you see, so F by 5 circuit, this is off for how many cycles? 4 cycles. This is on for one cycle. So suppose if you calculate the duty cycle, so 1 by 1 plus 4 into 100. Okay, you are getting 20% duty cycle. 1 by 5 means zero point 0.2 now. 1 by 5 means zero point 0.2. Okay. So you need to alter the frequency by how much? So from here you need to take out one cycle. Okay. Again you need to take out zero point 0.5 cycle. Okay. Suppose if you want to alter the output frequency by one cycle, you need to use which flip flop means positive edge trigger D flip flop. Positive edge trigger D flip flop. And next, if you want to alter the output frequency by zero point 0.5 cycles, you need to use the negative edge trigger D flip-flop. Negative edge trigger D flip-flop. Okay. So that outputs will be given to this OR gate such a way that you are getting F by 5 circuit. Okay. Uh, so number of flip-flops are increasing. By seeing this, can you say any optimization technique? Can we optimize? Can we decrease the number of flip-flops by seeing this table? Did you understand my question? So in order to see Q2, we can take Q1. Okay. So if you take Q1, that means this is off for how many cycles? 3 cycles. This is on for 1 cycle. So you need to alter the frequency by how much? 0.5 cycle only. So that you are using which flip flop? Negative H trigger D flip flop. So optimization will be happened. So in order to take as a Q2, I am taking as Q1. Okay, so that we are getting 50% duty cycle. So this is the optimization technique related to F by 5 circuit. Okay, so this is F by 5 circuit. Is it fine? How I am doing the optimization technique? When I am considering Q2, I am using two flip flops. One is positive edge trigger D flip flop and negative edge trigger D flip flop. So if you consider Q1, you can use only one flip flop. So that I can decrease the circuit complexity. I can optimize my design. Okay. So this is F by 5 circuit. Actually, F by 3 is same as F by 3 only. Mod is different. Again, I'm doing optimization. Suppose if you are taking Q2, you are using two flip flops now. So in order to decrease that, I am using only one flip flop. If I consider Q1, okay, yeah, yeah. So for this, I am writing the code. Mm, so F by 5 circuit. So for F by 5 circuit, what I need to do? I need to develop the mod 5 counter. Okay. So module divided by 5, 50 DC, input clock, input reset, output Y. So how many flip flops I need to use? Three flip flops. That's why count is what? Reg with a vector 2 down to 0 count. And here I am using the Q1 and Q2. No, that I am initializing with reg data type Q1 and Q2. First, I need to develop the modify counter. Okay, always at the rate passage of clock. You are getting modify counter. No, this is modify counter. Okay, always at the rate passage of clock or passage of reset. Begin if reset count equal to 3 tick binary 0 0 0 q1 equal to 0 else begin you are checking for the condition when count comes to 4 it should roll over to 0. Okay, it should roll over to 0 else count equal to 1 tick binary 1. Okay, so you are checking for you are developing the mod 5 counter and after that you are developing the negate of negative edge trigger D flip flop. So always at the negate of clock or passage of reset begin if reset. If I am applying the reset, Q2 is initialized to 0, else Q2 equal to Q1. That Q2 is giving to Q1. Okay. It's a sequential buffer only. No, whatever the Q1 is there, that is coming to the Q2. Okay. And at last, what I need to do? I need to I need to do the R operation. Okay. So that means I assign Y equal to Q1 or Q2. Okay. So this is my design. And coming to the test bench, so coming to the test bench, so module TV divided by 5, 50 DC. This is my module name. Clock and reset I am declaring with reg data type and y with y data type. I need to instantiate my design and generate the clock. Always hashtag clock equal to not of clock. First I am applying the reset. After 25 time minutes I am resetting the reset. I am running for 500 like 500 nanoseconds. Okay, dollar finish. Okay, so this I want to execute. So how to execute here? Just so this file name copy and give the create the design search. Next, create and choose the location, frequency divider, select OK, finish. OK, yes. Frequency divided by 5. Again, select all, copy. Again, you paste, save, and go to the test bench. Copy this module name, and next go to the simulation, add the simulation sources. Next, create and choose the location, frequency divider, select OK, finish, OK, yes. PB, frequency divided by 2 circuit. This code, select all, copy, and here you paste, save, and right click, set as stop module, run simulation, run behavioral simulation, save this project. So here expand this fit to page. Now you can zoom this, drag this side. Okay, just zoom this. So when reset equal to 1, what you are getting? Reset equal to 1, y equal to 0 only you are getting. So f by 5 circuit means it should be on for how many cycles? 2.5 cycles, no? So here this is one cycle, this is one cycle, and this is one cycle, and this is half cycle, 2.5 cycle. And next here also, this is one cycle, this is two cycle, and this is zero point 0.5 cycle. So this is off for 0.5 cycle, 2.5 cycle, on for 2.5 cycles, off for 2.5 cycles, so that you are getting 50% duty cycle. Is it fine? Do you understood? Yeah. So what is our conclusion? So we need to include the modern counter. If it is a positive edge trigger flip-flop, alter the output frequency by one cycle, one clock cycle. So negative edge trigger flip-flop, alter the output by half cycle. So need to choose the output of modern counter having a by n. Less alteration is required. Okay, that means hardware optimization we seen with F by 5 circuit. Similarly, F by 7 means what? F by 7 means same thing. So this is off for 4 cycles. This is on for 3 cycles. You need to alter the output frequency by zero point 0.5. It should be on for 3.5. It should be off for 3.5. So that you are using, first you need to develop the mod 7 counter, and next you need to develop a negative edge trigger D flip flop. Again, this is given to OR gate. You are getting 50% duty cycle. Okay. And this F by 2 circuit, this is off for the, so the up to here, till here we seen F by n circuit where n is odd. Okay. Next we are seeing F by n circuit where n is even circuit, even. Okay, n is even. So you need to develop F by 2 circuit means you need to develop mod 2 counter. This is off for one cycle, this is on for one cycle. So any extra circuit is required? No. Why? Because this is you are getting 50. Here itself you are getting 50% duty cycle. Okay. And F by 4 circuit also. This is off for how many cycles? 2 cycles. This is on for 2 cycles. Extra circuits is not required. Just if you develop mod 4 counter, then you will get this F by 4 circuit. Okay. So here I wrote the code for even and even also. So just if you see this F by 4 circuit, so simply you need to develop the mod 4 counter. Okay. So this you can check in the Vivado. So frequency divided by 450 duty cycle, input clock underscore in, input reset, output clock underscore out. So I'm declaring the internal count 1 down to 0. Assign count underscore out equal to count 1. Okay. This count 1 I need to assign. Why? Because Q1 I am using now. So that is count 1. Okay. And always at the rate passage of clock or passage of reset, begin if reset. If reset equal to 1, count becomes 2 tick binary 0 0. Otherwise, count equal to count plus 1. mod 4 counter 0 0 0 1 1 0 1 1, again it will roll over to 0. Okay, similarly test bench also you can develop. Okay, shall I show this, or you will see in the Vivado mod 4 counter frequency divided by 4? Waiting for your response. Yeah, yeah, okay, fine. Next you have this, we already see. So I'm closing this. I'll share this code, so okay, don't worry. Yeah. Next, frequency divided by 6 circuit. This is off for how many cycles? This is off for 4 cycles. This is on for 2 cycles. Okay. So you need to alter the output frequency by how much? 1 cycle. So to alter the output frequency by 1 cycle, you need to use positive edge trigger D flip flop. Okay. So that this will be on for 3 cycles. This will be off for 3. Actually, normally how much duty cycle you are getting? So that means 2 by 2 plus 4. Okay. So 2 by 6 into 100. So 1 by 3 into 100. You are getting 33.33% duty cycle. But you need 50% duty cycle. So that means here you need to alter the, here this is 4 cycles, this is 2 cycles. You need to take out 1 cycle from here. You need to add here. So that this is on for 3 cycles, this is off for 3 cycles. Okay. So you need to use positive edge trigger D flip flop. Positive edge trigger D flip flop. So here you see. So this is on for 3 cycles. This is on for 3 cycles, and this is off for 3 cycles. This is off for 3 cycles. So like this, you will get the F by 6 circuit with 50% duty cycle. For this also, I wrote the code F by 6 circuit. So here first you need to design the mod 6 counter. This is mod 6 counter. So input clock, input reset, output F6 underscore out. You need to declare the internal registers 2 down to 0 count Q3 and Q2. So you need to develop the mod 6 counter. So that means I need to check for the condition. So when the count becomes 5, it roll over to 0. Otherwise normal count. Okay. Next you need to design that count to you need and assign to Q2, and you need to develop the positive edge trigger D flip flop. Always at the right passage of clock or passage of reset begin if reset Q3 equal to 0, else Q3 equal to Q2. At last, what you need to do? You need to do the R operation. Okay. Assign F6 underscore out equal to Q2 or Q3. Okay. So here I'm not declared with red data type. Why? Because after the procedure block only I'm using F6 underscore out. I'm using continuous assignment statement. Okay. By default I'm not declaring any data type. It will take as which data type? Y data type. So I'm declaring this output with which data type? Y data type. So I'm using continuous assignment statement assign F6 underscore out equal to Q2 or Q3. Okay. So this is frequency divided by 6 circuit. Is it fine? Frequency divided circuits. Any doubts or queries? Okay. So this is about frequency divided circuits. Next we'll start with functions and tasks. Okay. Mm, yeah, yeah. Functions and tasks I will tell you. So functions. If you see the functions, okay. Uh, so functions. What are functions? Uh, so functions cannot have the delay statements. Okay, functions cannot have the delay statements. Functions are like nothing but suppose if you want to write, suppose you wrote 10 lines of code. The 10 lines of code, if you want to repeat for some like 5 times or 10 times, okay. So every time you can't write that 10 lines of code, no. So you are calling the, you can write the function one time. You can call for how many number of times you want to use, that many number of times you can call. Okay, that is function. Functions cannot have the delay statements. Okay, so function executed 0 time. So when it is executed, function executed 0 time. Function must have at least one input argument. It should have one input argument. Okay, so function should have at least one input argument. Function returns, always returns single value. So there is some return type. Okay, so normally in system Verilog you have void functions. So void function is means what, like in C language you have void function. No, it will return null. Okay, it will not return anything. But in Verilog, when you are using functions, it should return at least one single value. Okay, and functions cannot have output or input arguments. Okay, and functions cannot call tasks. Function cannot have output or input arguments. Function cannot call tasks. Okay, so that means function cannot call the tasks. Okay, and the functionality of task is same as function only. Tasks also will see. Function can call other functions only. Functions can call other functions only. Okay, so these are the important points related to these functions. Okay, so functions cannot have delay statements. Function should execute 0 time units. Function must have at least one argument. Function always return a single value. Function cannot have the output or input argument. Function cannot have call the task, and function can call other functions. Okay, so I wrote one program related to function, module function 1. I am declaring integer a comma b, function integer add, input add x, input integer y, add x comma y. Okay, so it will return which value. So there should be some return value. End function. I wrote the function. Okay, so module function. I wrote the function. Okay, this is for my function. Okay, after that initial begin, I am calling this function. There is a return type. What is my return type? B. Okay, function should have one return type. No, single value. Always return a single value. What is the value? It is returning b. B equal to add 5 comma 6. This is calling my function. Okay, I want to display dollar display. The value of b is percentage d comma b, end and end module. Okay, is this code is fine? Do you understood? Yes, yes, same as C only. Yeah, if you are comfortable with C, same. I told you, no, Verilog will support the C syntax. If you are comfortable with C, then functions you can understand easily. Okay, so here I am making this as top module. Run simulation, run behavioral simulation. So if you see the value of B in the code, what I given, in the code what I given 5 comma 6, no. So the value of it will add 5 plus 6 means the value of b is what, 11. Okay, is it fine? One more example also I wrote. See here, this is reg 3 down to 0 a. So module function example, reg 3 down to 0 a comma b, reg 4 down to 0 sum. So I am writing function 4 down to 0, add input 3 down to 0 x, out input 3 down to 0 y, begin add x plus y, end and end function. Okay, and next initial begin, I am declaring a equal to 7, b equal to 5, sum equal to what? This is a return type. What is my return type? Sum equal to add a comma b, dollar display a equal to percentage d, b equal to percentage b, sum equal to percentage d, a comma b comma sum. And again I am declaring two more values, sum equal sum. I am calling this function. These are the arguments. Okay, so a will be allocated with this x and b will be allocated this y. Okay, you are calling with these arguments. Okay, and dollar display, if I give one argument you will get error. Okay, I need to give how many arguments are there, that many arguments I need to call. Okay, dollar display a equal to percentage d, b equal to percentage d, sum equal to percentage b, a comma b comma sum. Okay, so this if I execute, right click, set as top module, run simulation, run behavioral simulation. So first A equal to 7, B equal to 5. I got sum equal to 12. And next I took A equal to 9, B equal to 6, sum equal to 15. Is it fine? Functions concept. Did you understood? Any doubts or queries? Shall I move forward? Yeah. Yeah, function is sequential. Yeah, yeah. Function is sequential. Yes. You are using blocking now, blocking assignments. That means sequential only. When you are calling this function, this will go to here and it will execute this. How many number of times you call, that many number of times it will execute. Okay. Yeah. So next is task. Okay. So the functionality of task is same as functions only, but here task can have delay statement. Functions cannot have the delay statement, but task can have the delay statement. Okay, task can be executed with 0 time units or it can have the delays also. Okay, so when you consider the delays, you need to use task. Okay, task have input arguments, output arguments, or it can have in-out arguments. Okay, it can have in-out arguments, and task is not going to not going to return any value. Okay, so function will is going to return at least one value. It should return one value, but task is not going to return any value. Task can call a function as well as another task. Okay, function cannot call the task, but task can call a function as well as another task. Okay, so these are the important points related to task. Did you understood the task? Is it fine? Yeah. So I'm writing the simple code for task. Module task 1, integer a comma b. Task add input integer x, input integer y, output integer result begin, result equal to x plus y, end task. Okay. I'm writing for task. Okay. Again in the initial begin, add 5 comma 1 comma b. Okay, 5 comma 1 comma b. So that means it is not returning any value. Actually this is 5 comma 1 comma, the result will be stored in b. Okay, again add 10 comma 20 comma b. Okay, the result will be stored in b. So I want to display this value, dollar display the value of b is percentage d comma b. Okay, so if I execute this, so task function set as stop module. So run simulation, run behavioral simulation. So you can see here the value of b is what, 6, the value of b is 30. So in the task what values I gave, 10, 5 comma 1 and 10 comma 20. So it is adding, and that values it is coming to the b value b. Okay, the value of b is 6, b is 30. Is it fine? Yeah. So which one in task you are asking? Parallelly, it's happening. So when you are calling this task, it will go here, and it will execute. It will execute, and again after that it will come and it will display this b value. I told you, no, Verilog is a contact. Yes, yes, it will act also in parallel. Every time when you are calling the task, it will go there, it will execute. Okay, it will execute this task, and after this, again it will come here, again it will display. When you are calling this, it will go here. It will execute this task. After completing this, again it will display. So concurrently, parallelly, it will execute. Okay. And next is there is a task-based test bench is there. Okay, so actually like in D flip-flop, how you wrote the test bench, normally this is the design. Okay, so I can write task-based test bench. This is the code for D flip-flop. Suppose the module D flip-flop, input Y, D input clock, input reset, output reg Q, always at the rate passage of clock or negate of reset begin. If not of reset, Q equal to 0, else Q equal to D. This is the design for D flip-flop. Okay. So normally in the test bench, how you given in the test bench? Suppose, 1 second, I will open the D flip-flop. Okay. Do you remember the test bench for D flip-flop? Do you remember the test bench for D flip-flop? Or why I will open? Okay, 1 second. Yeah. Okay. Just in the flip-flops, I'll open the flip-flops. Flip-flops, D flip-flop. So how you wrote the test bench? See here. So first, here what I did, first I applied the reset now. Applied the reset, and after this I am releasing the reset. Reset I am releasing, and I am giving the D values like this. D equal to 0. Wait for 10 and 12 time minutes. After that I am giving D equal to 1. After this, after 10 time minutes I am giving D equal to 1. Like this I am giving the inputs. I'm giving the stimulus to the design. Okay. So like this, I given the inputs for the D flip flop. Okay. Suppose if you take a task based test bench, open this, open this, Verilog programs, functions, function. So if you see the task based test bench, here how I'm giving means, so this is my task based test bench. Okay. So here module D flip flop, okay. Reg, so D clock and reset I am declaring with reg data type, declaring in the internal variables wire q, and you need to instantiate your design, okay. So design name, instance name, connection by name, initial begin clock equal to 0, forever, asterisk clock equal to not of clock. I am generating the clock, and I will write the separate task for the stimulus, okay, and also reset also, okay. So here this is for task for stimulus and giving the data and reset, okay. So task, apply. So what is my task name? Apply input, input reg din, input reg rin. Rin is nothing but reset in, okay. Rin is reset in. Begin D equal to Dn, reset equal to Rin. Okay. Wait for 10 cycles. Okay. And dollar display. I want to display these values. Okay. Time and D value, reset Q. Okay. I want to display this. This is dollar display. Okay. So this I wrote the task. Okay. End and end task. Okay. And next, to test the sequence, initial begin. First, I am applying D equal to 0, reset equal to 0. After 10 time minutes, I am applying the reset. Okay, after 10 minutes, I am releasing the result. Reset. How I am releasing? Apply underscore input. I am calling this task. Okay, I am calling this task. When I call this task, 1 comma 1. So D in I am giving as 1 and reset equal to 1. Okay. Next, apply the task. Apply underscore in D equal to 0, reset equal to 1. Okay. Again, so when you call this task, it will go here. It will go here, it will execute. Okay. Again, apply input 1 comma 1. So 1 comma 1 means, so D in equal to 1, reset equal to 1. Apply underscore input 0 comma 1. D in equal to 0, reset equal to 1. Again, if I want to assert the reset again, apply in 1 comma 0. Reset I am giving as 0. Okay. After that, I am releasing the reset. Apply input 1 comma 1. D in is 1, reset is 1. So this is task based test bench. Like this, you can write the task based test bench for SR flip flop, JK flip flop, any flip-flop also, counters also. Okay. So this is task-based test bench. Suppose if I want to execute, just right click, set as stop module, run simulation, run behavioral simulation. So you can see in the TCL console also. D equal to 1, reset equal to 1, Q equal to 1, D equal to 0, reset equal to 0, Q equal to 0, D equal to 1, reset equal to 1, Q equal to 1, D equal to 1, reset equal to 1, Q equal to 0, D equal to 0. So D equal to 1, reset equal to 0. As D equal to 1, reset equal to 0, it will go to the reset state. Again D equal to 1, reset equal to 1, Q equal to 1. You can see in the simulation also. So you can see in the simulation here. So when D equal to every time means I need to see. So clock D equal to 1, Q equal to 1. Okay, and during this clock, okay, D equal to 1, Q equal to 1. Again D equal to 0, Q equal to 0. Again D equal to 1, Q equal to 1. And next D equal to 0, Q equal to 0. So when the reset is applied, here reset is applied. Even though D is 1, I am getting Q equal to 0. Okay. So irrespective of clock and reset, it will force the output to what? 0. Reset is applied. And here during this clock edge, D equal to 1, Q equal to 1. So like this, I can see the waveform. Did you understood the task-based test bench? Is it fine? Any doubt? Yeah. Yeah. So with this, we completed the whole RTL concepts. So next week I'm planning to tell two projects related to this RTL. One is I2C project, next one is a UART project. Okay. Yeah. Yeah. Any doubts or queries related to this? Okay. So, okay.